Hi everyone, in today's video we're going to make a Boggle solver using some classical AI algorithm and some clever use of dynamic programming. This is a very good project for beginners because it teaches you a lot about optimization, about search, about data structure, graphs, and it's kind of fun to see it in action in a real world scenario with a real board game. So before we're gonna jump into the project, let's do a bit of a refresher about what Boggle is. So basically you have a 4x4 grid, sometimes 5x5 or 3x3, and it's a bunch of dice. And then if it's a physical Boggle game, you're gonna shake the dice like this, they will shuffle, and then you'll be able to have letters. And then on each of these dice there's different letters, so it's a bit random, the distribution of letters you're gonna get. And the game is that you have 2 minutes usually to find as many words as possible. And to find word, you have a letter here. You can move in eight possible direction. So up like this, like that, to the side, down. In all of these direction you can move. And then the goal is to make a sequence of letters that turns out to be a word. You cannot go back to a letter that you already used. So once you use letters, you have to continue moving. And that's it. The longer the words, the higher the point that you score. So if I were to actually make word here, you see I've started a bunch. Let's take a look. What can I do? Sat, maybe? That's a word. I suck at this game, honestly. Tin, I think is a word. Yeah, tin with an S, maybe. Yes, wow, okay. So that's, you've seen it a bit of in action. And you have to find as many words as possible as you can. So that's kind of the game. Let's actually make an algorithm now that can do that automatically and find all of the word under 2 minutes. So we are in the right folder, and I will be able to call the main file that holds basically the algorithm to find all of the word in this Boggle game. And if you see here, I'm using as an input boggle44.txt. It's my way of encoding the board letters. Yeah. So if I run this, you're gonna see a bit of debugging output, but then you'll see all of the words starting to appear, and it took 5 seconds to run. So if I look at some word, let's say density, here it will be this way, density. Poof. And that's it. That's kind of how the thing works. Okay, so let's look at our strategy a bit. In order to solve the Boggle board, we're gonna do a 3-step. The first step over here is to find a dictionary to validate the word. If we don't have a dictionary, it's impossible for us to decide if a character string that we've done is a word or not. So this is the first step, pretty standard. And once we have this dictionary, what we're going to do is we're going to build a trie structure to search efficiently the board. Now, this is important because if you look at the 4x4 grid that we have, it will be very difficult to do all of the possible combination for each of the possible word every time, right? If you can kind of go with a pen and paper through it, it will be too lengthy. We only have 2 minutes in order to find all of the word before the game ends. So as you've seen in my example, the code ran in 5 seconds. In order to do that, you have to do some dynamic programming in order to do as less as possible of repetitive tasks in order to find all of the sub-answers that you need. The way to do this is by building what we call a trie and encoding the dictionary as a trie, and then to search through the dictionary using the letters, the starting letters as the seed in that search. This way you'll be able to chunk down the amount of searching that you have to do by a lot. So this is the second step, is to actually build the trie, and this step over here is not dependent on the board game that we have. So we do that work all prior than the game starting. So this will help us to be more efficient. And then the last thing is to actually traverse a board game, the Boggle game as a graph, and then using the trie to speed up the search by a lot. You might ask yourself, what is a trie? The trie is like this. It's a data structure that looks like that. It's a tree structure, right? Specifically, we're in a trie, we're encoding characters. Yeah, and then there's a structure to it. So the way we're gonna do that is by having our root over here, which is nothing. And then if you see, there's all of the alphabetical letters here. So A, B, C until Z. And this letter A then has all of the letters A, B, C, Z attached to it. And then that AA has A, B, C, Z attached to it. And then it just recurs like this infinitely if we want to. But the interesting thing is, by using the dictionary, we're gonna prune these connections to only keep them that makes up a word sequence, right? This is important. If you look at an example with the word apple, how it will be encoded into our trie will be like this. So we're gonna have the root here, and then we're gonna have at the first level A, and then we're gonna have a simple flag that check if this is a word. A is not a word, it's a letter. And then you're gonna have AP, and then the node over here will decide if it's a word or not. App is not a word. Then APP, and then APPL, APPLE, and this is a word. So that here we define that this is a word, and then APPLES, and this is also a word. So it will be defined here. But all of this, we're doing this prior with the help of our dictionary. So to do that movement, there's two things. First, we're gonna go through all of the possible connection in this trie, and then we'll check out into the dictionary if this letter is even possible. And effectively what we're gonna do is all of the connection lead to a word. So if we're in a Boggle game, what we're actually gonna be doing is we're gonna go for, let's say the first letter is A, we're gonna go for A, and then we're gonna search all of the different connection depending on the board. And then if, for instance, there's a path from A to S that make apples, through our search, we're gonna find it. And then we're gonna do that thing in the board and then do that movement into the trie also. So let's actually jump into the code now to see what it looked like in action. Perfect. So here we are in the code base. It's pretty standard stuff. I have a bunch of things here, but it's the three things that are mostly important is the English dictionary.txt file and those two files, the build trie and the main.py. Everything else is just here to scaffold and help a bit. And the boards are over here. So if you look at the boards, it's just a comma separated value. It literally like a Boggle board, and this is what we're gonna use. The first step in our strategy in order to do that AI that is able to read a Boggle game and then to give the answers is to find a suitable dictionary. I found one over here at this GitHub repository, and it looked like this. So it's really a text file with each line being a word. That's it. There's a lot of word in there, and it's suitable for our stuff. Some words are a bit weird, but for demonstration purposes, it's good enough. So this is step one. We've done it. Let's go into step two, which is to build a trie. Here we are in this file, specifically the build trie.py file. And I'm going to walk you through the whole code base over here. There's two files that we need to look at for this one, build trie and data structure. And with this, we'll be able to actually encode our English dictionary into the trie that I showed you earlier with like all of the nodes. This is kind of what the headers is looking like. I have my dictionary name as a constant. My letters here, there's a better way to do it, but I just put all the letters from A to Z. And here, if you see, I'm importing a data structure called node, which is what my trie node will look like. And then I just need a node, I'll need a trie structure because I'm gonna stitch node together to actually make my trie. So if we jump into that, the node class is fairly standard. There's nothing in it. It's just like an actual node. There is information on it. There's the letter that is containing, that the node is containing. There's edges. So here a node can have up to 26 edges if, for instance, this letter have all of the possible letter in the alphabet as next word in a sequence. There's this attribute is word that is important because it will define what in each of the path amount to a word. And then sequence, I'm storing like all of the previous letters in here so that I can print it better whenever I'm gonna traverse. And this is just like the initializer. There's nothing much here going on. So a node, the connection are encoded as a dictionary. So now I can do like edge bracket A, and then I'm gonna go into the A node directly. So that's that. And if we look at the structure for the build try, I have my main function here. The first thing I do is I load the dictionary file, which is this, and I just load it and put it into file data, and then I'm gonna give it into this function that we're gonna see in an instant. And my try over here, I'm just gonna populate it, create it as the first root node. So this is actually the root that I've talked about when I was showing the diagram, right? And the root has nothing in it. It's just a way to hook it and then to be able to go through one of the letters as a first traversal. And at the end, I just pickle the whole dictionary try object so that I can reuse it into my main.py file. So far so good. It's not too complicated. Now let's look at populate try. And if you see, there is three things that we're giving: a sequence, a dictionary, and a subtree. The sequence for now is this. It's just the root. File data is my dictionary, and try is my subtree. Because I'm gonna take the try and then I'm gonna populate it by going into different section of the try. At the beginning, there's nothing except the root, and then I'm gonna go and then do all of the different permutation. This is a recursive function, so buckle up because it you need to think about it as a recursive function. It just keep on going within itself. Let's take a look at populate try. It's this whole thing is just one big for loop, right? Yeah, and it just call itself again and again and again, and it ends when it did the whole range of letters. So if we look at it step by step, just make some space here. So the first thing we're doing is we're iterating on each of the letter in the alphabet. So that alphabet over here, right? And we're iterating on it, and like I said, it stops whenever there is no more letters. So at Z, if nothing happened, we move out and then we jump back up. So what we're doing at first is we're creating the new sequence based on the current sequence that we have here. Remember, it's recursive, so you have to think about it as at any point in time, it will have a sequence of any sort. It doesn't have to be the root here all the time. So I'm creating the sequence by literally just appending the letter. I think there's a better way to do that than just to give index and stuff, but it doesn't matter. I'm making the new sequence, and then I'm calling this function get subdirectory. And this function, what it does is it takes the directory, so the thing that you give, and then the new sequence, and it will give you this dictionary, but like cut, so that you only have the part that start with your sequence. So if your sequence is AB, it will cut everything that is not A, that doesn't start with AB, and it will keep doing this recursively as you're going through the building of the try, right? So if you look at it, the get subdirectory is fairly simple, right? You have I'm creating a subdirectory, subdictionary here, and then for all of the word in the current dictionary, I check if the word that I have in the dictionary start with the sequence that I have, and if I do, I just append it, and this is what I return. Fairly straightforward. I'm just like taking my dictionary, cutting out, so that I can put the right stuff, search only on the right stuff. If the new subdirect dictionary is empty, I don't do anything, I get out, right? So if let's say there's no word that starts with AZ, I'm just not gonna go further and test everything. I'm just gonna get out and then go into the next situation. But if there is, it means that there's words that we need to encode, letters that we need to encode in here in our try, right? Because remember, the whole point here is to encode it in our try. I first check if the current sequence is a word, right? Because remember, let's say apple, apples. When you're gonna go through apple, this is a word. It should be encoded in the node as such, but you should keep on going so you can continue to get apples, and you should do that all the time to always encode the right word. So if we look at this again, this one is also pretty straightforward. I check all of the words in my dictionary, and if the word matches the sequence, I return true, otherwise I return false. Which means that I check my dictionary completely, the subdirect dictionary, the one that is smaller, and I check if this word that I have here is in my sequence. And if it is, I'm just gonna print it just for visual sake. But the most important thing is I'm gonna put that information into my node. You see here, I'm gonna put the letter in my node, right? The letter I'm at right now, the new sequence that is a bit bigger, which is a word or not, and the fact that it is a word or not. If it's a word, this will be true. If it's not a word, it will be false. And I will add that in the subtree that I'm making, which is a try. In the edge, I will encode it as a key in the dictionary and put that node over there. And I recurse. It look a bit like magic, but basically it will create the tree and then start with all of the A's, and then when it's done with the A's, it goes all to the B's, and then it goes through the C's. And every time we're always looking at the dictionary in order to populate this try properly. So if we want to look at it in action, let's take a look. You see, I'm doing all the A's, I'm done. I'm doing all the B's, I'm done. I'm doing all the C's, done. D's, E, F, and then it will just iterate like this. And all of this is getting encoded, right? And it will get encoded into my try over here because it's an object, and I'm passing an object over and over again, and I'm not making copies of it. So all of the addition I'm doing into the edges, it will get recorded into the object. So if I have a whole of the first node, I get all of the other objects that are getting created because they're all attached to data structure in the over the edges. And then I just save that dictionary try obj. I saved that over there. This we'll be using it into the main.py that will actually go and solve the Boggle game using the try. Okay, so here we are on the main file, and if you saw the previous part, we're calling it like this, main.py, and the name of the file containing the Boggle board. The Boggle board are looking like this. This is for Trie, this is for 4x4. Already seen it, so we can dive into the code. Okay. So I have a whole bunch of import that I will need afterward, and I'm importing my data structure node just because I'm gonna load a try and then use it. So if we look at the main function, I have a timer that I start and that I end over here just to kind of check out how long it took to run this algorithm. Just to be sure that I am under 2 minutes. I need to be under 2 minutes. There's a bunch of error checking for the argument, but everything happened over here, right? So if we look at the end, I'm gonna print all of the word that I'm able to find. This is the last thing that you see. Over here, I'm creating what we call a grid. So the grid is the Boggle board, and then it will hold every information I need from the Boggle board. I'm gonna print a bunch of stuff, and finally, before starting, I'm just gonna go, before outputting the word, I'm gonna find all the word, and then I'm gonna output it. It looks really straightforward because everything is happening on the grid, literally. So let's look at this. The grid will get as the argument the file path for the dictionary. If we look at that, this is the grid, right? This is the grid class object. I have a bunch of letters in the grid, so this is my 9 letters. I have the dimension, 3 or 4, maybe 5 sometimes. This is the node, and this is the adjacency matrix. There's a difference between the grid right? The 4x4, and the graph that is created by all of the nodes. There's 9 nodes in the Boggle game, right? There's 9 nodes, so the index 0, 1, 2, 3, 4, 5, 6, 7, 8. And then these nodes are connected as a graph. This is an important distinction. We'll see it in a minute what it means. And then there's the output words that goes in here. So let's say you have a grid like this, right? So A, B, C, D, E, F, G, H, I, right? You have that. Now what will happen is that I will encode this and keep the letters, but that's not how I'm going to solve the problem because it's very difficult. Remember in the Boggle you can move this way like this, you can move this way like that, like this, over here, here, in all directions like that. So a direction. Sometimes you cannot, right? There's nothing to do here. Sometimes that you can't, you're going to be up, but sometimes you can, like in this direction. Yeah. But in order to encode all of this this movement, the best way is to actually view this as a graph and then use what we call an adjacency matrix. So for instance, you have to encode the fact that you can go all of these way, but that you cannot do that. This is not permitted into that game, right? So we have to find a way to encode this that is super easy so that we can reuse it afterward. And we'll simplify greatly our code if we do that. So this is actually my my graph. It looks really similar to this. There's no concept of a board or Boggle, it's just a graph. And then I start to put my connection in place, right? So the connection look actually like this. There are bidirectional connection, and it make it so that everything will be neatly connected together. So what I mean by bidirectional is that B and C are connected, not just like this, but actually like that, right? In both directions. So I connect everything faithfully like this. And ta-da! This is beautiful. These are all the connections that are possible. Missing some here and here. All the connections that are possible in this board. Now this, the computer doesn't understand still, but it understands adjacency matrix pretty well. So it looked like that, right? And how we're gonna fill this thing, this grid, will tell the computer what is connected to what. So if we look, there's no connection like this, right? There's no self connection. So all of the middle row at the diagonal have to be zeros. So zeros mean that A and A are not connected together, and then B and B are not connected, and everything like this. I'm not gonna do the whole thing, but you get the point of it. I'm just gonna do A. So if you look A, is A connected to B? Yes. So this is there's a 1 going there. Is B connected to A? Yes. So if you look at the matrix, it will be symmetrical. Now, is A connected to C? Of course not, because you cannot jump that far. The only thing that is connected still is D and E. So this is 1 and 1, and D and E also are connected to A, and we have it fully over here. So this way of representing the whole the whole graph will be very useful, because the first thing we're going to do in our code is go from this all the way to this in order to have a fantastic representation of our graph that we can use for many for the rest of the traversal. So now that this makes a bit more sense, let's look at the constructor which will create this adjacency matrix. So the first thing we're going to do is we're going to open up the Boggle file. This is the Boggle file, same code as I did in the other one, but this is the Boggle file that we're opening. And then the second thing we're doing with the Boggle file is we're going to read all of it, and then we're going to store the stuff. So we have the file, we're going to split the columns, which are separated by the comma. So we're going to get all of the letters, and we're going to get that put into letters over here, and then I'm going to iterate on each of the letter in that column, and then put that into the nodes. So I'm going to put this in each of the nodes, and remember the nodes are just an array here, and and then I'm gonna set up the dimension to be how many letters there were in one row. Here in the last portion over here is the rest of my constructor, and what we're doing is we're gonna create the adjacency matrix. So basically I'm gonna iterate on all of the rows and all of the columns and each of the nodes, and then I'm gonna calculate with what they are connected, put that into the adjacency matrix. So I have this nice formula over here that will give me from the row and column index, the actual index of my node, because it's in a 3 by 3 I have 0, 1, 2, 3, 4, 5, 6, 7, 8. That's the index of the nodes. So the formula is row times in a 3 by 3 3 plus the column I. So if we take the first one, top left, it will be 0, 0. I'm gonna get 0 times 3 plus 0, this is 0, cool. And then the last one is 0, 1, 2, 3, 4, 5, 6, 7, 8, 8. So I have 2 times 3, because it's the row number 2, times 3 number of dimension, plus 2. I have my indexed 8, so this is perfect. So I'm gonna calculate the current index of my node, because I never know where I'm at, and then I'm doing self.adjacency matrix. So I'm gonna append false for everything in this current row in the adjacency matrix. So I'm going like this. So to build it, I'm going like this. So at first I'm gonna put everything to 0, and then I'm gonna check where it's actually true, and then I'm gonna do the second one, put everything to 0, check where the thing is actually true, the connection. Okay, so once this is set up, now I need to check out what is actually connected to what. And then to do this, I'm gonna recreate the movement in all 8 directions, right? So technically what I can do is I can move up by doing -1 on the row. I can stay there and go sideways, or I can go down and I can mix all of those 3 possible combinations. So I can do 9 action, right? I can go up like this, go like this, go like that, go like this over here. I can also stay where I'm at. But this is not allowed in terms of connection, and etc, etc. So I'm encoding the movement for each of the thing, and then I'm checking if I'm out of bound. That's literally what I'm doing. So if I'm out of bound, let's say in the next row that I'm going, let's say the smaller than 0 or greater than the or equal than the dimension, I just skip this one. I keep the false in. And I'm doing the same thing in the column. If I'm out of bound in the column, it doesn't matter. So yeah, and then here what I'm doing at the end is at this point in time the actual step I'm taking is possible, so there's a node next to it, and I'm checking this node. I'm using my function, and then I check if this node is the same as the node that I'm currently at. So 0, 0 move, so a move on itself. If this is where I'm at, I just skip because this is not allowed. I let it to false. Otherwise, I can reach that node and I'm gonna put it to true, right? So this is what you see when you run the code at first. So if I do this, right, the first thing you're seeing here is the adjacency matrix that I'm printing. So for this board, the 4 by 4, you have all of the 4 times 4 nodes over here and down here, and then you can see the diagonal here is always false, like that, right? So this is what I'm doing in my constructor. So that's for this part when I'm creating it, and I'm gonna print grid, print the adjacency matrix. This is what we've seen just here, but it's not we're not gonna go look at the code because it's just like aesthetic, just so I'm able to see the stuff and debug. The important part is here in the grid and find all words. So let's look at it. Here we are at find all words. So the first thing we're doing is we're going to load the trie and we'll put it into a tree, and then we're going to iterate in each of the node in our grid. Right, this is what we're going to do. And I'm going to extract the letter, and then I'm going to take the full trie and then just take a look at the chunk that starts with my letter. So I'm already moving like this in my trie. This is how I move. I just take a subtree and I'm gonna keep taking a subtree, and then further on you'll see I'm gonna check out if the place I'm at is actually a word or not. Before going into my recursion, which is what the depth first search graph function is, because I'm doing a depth first search, I'm gonna make a copy of the adjacency matrix, because you'll see what happened as I'm making the move. So here I am into my my graph. Let's say we start here at A. The first thing I'm gonna do, let's say I'm gonna be in A. I'm gonna save this graph because I'm gonna do a bunch of stuff to it when I'm gonna be in it. So the full movement will be like, okay, I'm at A. Now I need to move. I'm gonna move at B because it's the closest. I'm gonna do that move, but before doing it, I'm gonna do this thing. I'm just gonna cut everything else, right? So what it means is that once I'm gonna be at B, I'm not gonna be able to come back to A, right? It's impossible. Let's say I'm gonna move to E afterward. Let's say first thing I'm gonna do before jumping is cutting all of the B connection to everything else. So what will this effectively do is it will allow me to not go back to A and B. Remember, Boggle, you cannot come back to the letters you already used. So then I'm gonna chug along over here, and then at some point I'm gonna be out of move, and then I will need to backtrack. Let's say I'm done with E, I will need to backtrack and restore that image so that I can then go to C, and then before going to C, I'm cutting all ties and I'm doing this. You see, so that's the movement I want to get going. And then once I'm done with everything having to do with A, I want to do the same thing with B. So I'm gonna start with B. Let's say I want to move this way. Then I will need to cut all of these ties and then do the A. So that's what we're looking for in terms of motion. Remember this, because this will be used in a moment. And I'm gonna jump into the depth first search graph. And in the graph, we are at a specific node. There's the adjacency matrix that tell us like how to move stuff. And then there's our trie or sub-trie that is in there that will tell us like what is a word and what is not. So this part is where the magic actually happens. This is where we define if something is a word or not, right? So the first thing we're gonna do is, because the movement into the Boggle board and the movement and trie are synchronized, if in the spot that I'm at in this sub-trie is a word, the node that I'm in, it means that this is a word in a dictionary, right? So this is important. I'm gonna put it into the output words, but I'm also gonna check if it fit some of the rule, that namely that the word is bigger than Trie, and that the sub-tree, that sequence, that the word it is not already in the self.output words. This happens if this whole thing is true, then it means that this thing is a word greater than Trie, and I've never seen it before. I'm gonna put it into output words, and this is what we're filling it up in order to print it. And then we're gonna iterate on each of the connection from this position that we're at, right? And I'm gonna go through all of the nodes that are possible, but I'm gonna first check if there's a connection, if this in the adjacency matrix and the current index and next index are true. If it's not true, I don't care. I'm just gonna go through the next node. If it is true, then I'm gonna do my cut dive move. So the cut dive move is I make a deep copy first. And for this node that I'm at, I'm gonna cut every connection by setting them to false with every other node. So I'm never gonna come back to it again, right? But when I'm gonna come back from the backtracking, it's gonna be restored because I'm gonna use this and not that in this iteration. So this was my cut motion, this is my jump motion. And how I'm gonna jump is, I'm gonna check if in the subtree that I have left, the letter that I have right now, let's say we're A, B. If B is not in the subtree, there's nothing to do. But if my letter, let's say was B, is in the subtree that I have, then what I'm gonna do is I'm gonna take that subtree, starting at my B, right? I'm gonna store it, and I'm gonna recurse with all this new information. The next index where I will be, the new adjacency matrix that I've done with the edge cutoff for the current node in this recursion, and the new subtree, which is smaller, that start at the node. I would be in that new move, and that's it, right? There's nothing else here. It still look like magic because this is recursion, right? So my stopping, my stop for the recursion happen over here when I'm out of nodes, right? And it doesn't go into an infinite loop because I'm gonna only move here if there's a connection, and at some point there will not be. And here, this is where the magic happens and where I'm actually saving the output. So that's it. And if you look at the whole thing in action, it will look like this. You see, this is my board, this is my adjacency matrix, and then we'll start to go through it and then have all of the sequence of words that are possible from the Boggle game and from the Trie, and it will use that. All right, everyone, I hope that you enjoyed this walkthrough of the project. Let me know in the comment if you have any question, and if you want to check out the code, you can go into the description and check out the source code. So I wish you all a fantastic week.